Welcome dear learners. We are continuing Unit 3, Introduction to Nanomaterials. The title of this module is Metal Oxide Nanoparticles Part 1. The contents we are discussing here are Introduction to Metal Oxide Nanoparticles, Characteristics of Metal Oxide Nanoparticles, Zinc oxide nanoparticles, its synthesis and properties. Iron oxide nanoparticles, its synthesis and properties. First of all, introduction to metal oxide nanoparticles. Metal oxide nanoparticles are nanoparticles with at least one dimension in the nanoscale range, that is 1 to 100 nanometer. We all aware about nanomaterials. Nanomaterials are materials in which at least one dimension, that is either along x direction, y direction or z direction, should be in nano regime. Nano regime means the nanometric measurement or nanoscale measurement. It lies in the range 1 to 100 nanometer. These metal oxide nanoparticles have unique properties due to their small size and high surface area. This make them highly different from the bulk materials or bulk counterparts. It is a very general characteristic feature of nanoparticles that there is associated with high surface area. And this high surface area is a direct outcome of their small size. So, high surface area along with the small size make metal nanoparticles highly different in their physicochemical properties compared to the bulk material. Now, some examples of metal oxide nanoparticles. Most of the metal can form their oxides. However, metal oxide nanoparticles cannot be formed from all the metals because some metal oxide nanoparticles are highly unstable. Here we are discussing some examples of stable metal oxide nanoparticles. The examples include iron oxide nanoparticles, which may be Fe2O3 or Fe3O4 in composition. Now, zinc oxide nanoparticle, abbreviated as ZNO, titanium oxide nanoparticle or TiO2 nanoparticle, it is otherwise known as titania nanoparticles. They are stable nanoparticles, stable metal oxide nanoparticles. Cerium oxide nanoparticles, etc. are good examples for metal oxide nanoparticles. So, every metal can form their oxides. However, every metal cannot form stable metal oxide nanoparticles. This is because many of the metal oxide nanoparticles are highly reactive, or they cannot be prepared by simple methods, or they require special stabilization methods. And these are examples of some stable metal oxide nanoparticles which can be prepared by popular methods, characterized by common methods, etc. Now, these metal oxide nanoparticles have unique properties that make them useful in many fields. That is, these metal oxide nanoparticles have diverse applications. Let us look onto some important applications of these metal oxide nanoparticles. The metal oxide nanoparticles are useful in water purification and pollutant degradation. See, for example, titanium dioxide is a very good photocatalyst which is highly useful to remove pollutants like organic dyes, and it is helpful in water purification. Another application is in drug delivery systems. For example, magnetite nanoparticles, its chemical formula is Fe3O4. The magnetite nanoparticles are useful in drug delivery systems. How nanoparticles can act as drug vehicles or how they perform in drug delivery. It is possible to anchor the drug molecule onto the surface of the iron oxide or magnetite nanoparticles and some other nanoparticles also. There are so many nanoparticles which prove their efficacy in drug delivery. Here we are focusing on iron oxide nanoparticle. See, this magnetite or Fe3O4 nanoparticle, let its surface is modified and some drugs are loaded onto the surface of that magnetite nanoparticle. This magnetite nanoparticle exhibits prominent magnetism. Whenever it is injected onto the body, that magnetic nanoparticle along with the drug can be moved through our veins. This movement can be controlled by the application of an external magnetic field. So, this iron oxide nanoparticle along with the drug will move selectively through the veins and reach at the site where the drug is required. At that site, this metal oxide nanoparticle releases the drugs which is placed on the surface of that. This is the mechanism of drug delivery. So, magnetic nanoparticles like magnetite or Fe3O4 is highly useful in drug delivery systems. Now, the metal oxide nanoparticles are useful in photovoltaics and solar cells. What are photovoltaic devices? You are familiar with that. These are devices which convert energy from a photon, that is energy from light, into electricity. Solar cells are light energy harvesting devices. The incorporation of metal oxide nanoparticles such as titanium dioxide and zinc oxide into the solar cell components increases its efficacy. So, this incorporation of the metal nanoparticles make solar cells more effective in energy production. Thus, photovoltaics and solar cells are very recent, highly important applications of metal oxide nanoparticles. Now, batteries and supercapacitors, these kind of electronic devices can also be generated from metal oxide nanoparticles, or you can incorporate metal oxide nanoparticles like MnO2 to improve the performance of batteries and supercapacitors. Catalysis in chemical reactions. There are so many metal oxides that proved their efficacy in catalysis. You know, a catalyst is a species which is capable of altering the rate of a chemical reaction without actually participating in it. The metal oxide nanoparticles are associated with a small size and hence very high surface area. That improved surface area enhances their catalytic performances. So, many metal oxides like cerium oxide are highly useful as catalyst in chemical reactions. Specifically, cerium dioxide nanoparticles are used in pyrolysis or cracking reactions. Now, abrasives and coatings is another prominent application of metal oxide nanoparticle. Aluminum oxide nanoparticle, due to its hardness, it can be used in abrasives. These are materials used to smoothen some surface. So, aluminum oxide nanoparticle, owing to its hardness, it is useful in abrasives as well as it is useful for coating some surfaces. Now, antimicrobial coating. We are familiar with the fact that silver nanoparticles, we learned in previous modules, silver nanoparticles exhibit antimicrobial activity or antibacterial activity. There are some oxide nanoparticles like zinc oxide and copper oxide nanoparticle which can prevent the growth of microbes, or such metal oxide nanoparticles have antimicrobial activity. So, these materials can be used for antimicrobial coating. Now, we are focusing on characteristics of metal oxide nanoparticles. What are the important characteristic features of metal oxide nanoparticles? I already mentioned the fact that bulk metal oxide and nano metal oxide are entirely different in their physical as well as chemical properties. The physicochemical properties of metal oxide nanoparticles are highly different from that of bulk material. This is owing to two important parameters. The first one is high surface area and the second one is the quantum confinement effect. So, high surface area is a direct consequence of small size. Nanoparticles have a very small size. They are associated with the high surface area. High surface area along with the quantum confinement effect make metal oxide nanoparticles highly interesting and their physicochemical properties entirely different from that of the bulk material. Now we are focusing on what are important characteristic features of the metal oxide nanoparticles. The metal oxide nanoparticles exhibit unique properties owing to small size, large surface area. Distinct physicochemical characteristics are owned by them. Some important general features are described here. The first one is nanometer scale. It is very well clear that the metal oxide nanoparticle exhibit size in the nano regime. Their size typically 1 to 100 nanometer leads to quantum confinement effect. This quantum confinement effect have a strong influence on electronic, optical as well as magnetic properties. The second characteristic feature is their surface area. I mentioned the fact that the metal oxide nanoparticles are associated with very high surface area. High surface to volume ratio is also their characteristic feature. This high surface to volume ratio enhances reactivity, make them suitable for catalysis, photocatalysis and adsorption applications. You know, adsorption is a phenomena that is occurring at the surface. High surface to volume ratio is a supporting factor for adsorption. So, these metal nanoparticles have strong adsorption capabilities, catalytic capabilities as well as they can be used for photocatalyst. Next characteristic feature is associated with the stability of the metal oxide nanoparticles. Moving on to the stability, the metal oxide nanoparticles are chemically stable. Not all metal oxide nanoparticles, most of the metal oxide nanoparticles are highly stable. At the same time, some metal oxide nanoparticles are highly reactive also. In a general way, we can say like this, most of the metal oxide nanoparticles are chemically stable. And how this chemical stability happens? The chemical stability is due to resistance in oxidation behavior. The metal oxide nanoparticles are obtained by the oxidation of metal. So, metal oxides are present. Here the metal is already in positive oxidation state. Metal is already oxidized. Since metal oxides are already oxidized compounds, they will not undergo further oxidation. That means there is a strong resistance towards oxidation. This imparts high stability to most of the metal oxide nanoparticles. Now, redox activity is another characteristic feature. Many metal oxides such as ceria or cerium dioxide nanoparticle, magnetite or Fe3O4 nanoparticle can participate in several oxidation reduction reactions. And that oxidation reduction reactions have some crucial role in environmental and biological applications. You are familiar with the redox reactions. What are redox reactions? These are the reactions where oxidation and reduction happens simultaneously. There must be an oxidizing agent as well as a reducing agent in such a redox reaction. In metal oxide nanoparticle, the metal are present in positive oxidation state. So, they can undergo some reduction reaction. So, in the presence of a reducing agent, this metal oxide nanoparticle can undergo a reduction reaction. At the same time, some metal oxides nanoparticles contain metal in their lower oxidation state. They can undergo further oxidation reaction. This means the metal oxide nanoparticles generally undergo reduction reaction, but some metal oxide nanoparticle can undergo oxidation also. So, in the presence of a reducing agent or an oxidizing agent, the metal oxide nanoparticles can undergo redox reactions or in general oxidation reduction reactions. This come under the title their redox activity. Now, the next feature is their crystallinity. You know about two kinds of materials. They are amorphous solids and crystalline solids. The amorphous solids and crystalline solids have so many differences in their physicochemical properties. For example, glass is an amorphous solid. At the same time, sodium chloride is a crystalline solid. Glass is associated with not sharp melting point. However, in the case of sodium chloride, there do a sharp melting point. So many other differences like isotropy, anisotropy, etc. are there that you have studied in your school classes. And we are now focusing on the crystallinity of metal oxide nanoparticles. The metal oxide nanoparticles exhibit strong crystalline nature. These particles often exist in various crystalline phases also. See, for instance, titanium dioxide nanocrystal or titania nanoparticle can exist in different crystalline phases. The two popular crystalline phases associated with the titania nanoparticles are anatase phase and rutile phase. That is, you can prepare titanium dioxide nanoparticle, it crystallizes in either anatase phase or in rutile phase. And this crystallinity or crystalline phase also have strong influence on their physical and chemical properties. So, most of the metal oxide nanoparticles exhibit well-defined crystallinity and they have distinct crystalline phases also. Now, band gap tunability. We know the fact that in the case of a semiconductor nanoparticle, there occur some energy difference between the valence band and the conduction band. Theoretically, that energy difference is known as the band gap. The band gap of a semiconductor nanoparticle and in the case of metal oxide nanoparticles also, the band gap has a strong connection with the size of the nanoparticle. Several metal oxide nanoparticles exhibit size-dependent band gap shift. That means if you are changing the size, the band gap also changes. So, by tuning the size, it is possible to alter the band gap of many metal oxide nanoparticles. So, a controlling on band gap enable their applications in different areas such as photocatalysis, UV blocking material preparation, etc. For instance, zinc oxide nanoparticle can block ultraviolet radiations. So, it is used in protecting materials, UV protecting materials, used to develop several kinds of UV protective materials. This is because of the fact that certain sized zinc oxide nanoparticle can absorb harmful ultraviolet radiations. Their photocatalytic activity also relies on the band gap. So, band gap is tunable by size. If we change the size, band gap changes. So, with a suitable band gap, we can experiment that material for photocatalysis. Another characteristic feature of metal oxide nanoparticle is its hydrophilicity. What do you mean by hydrophilic situation and hydrophobic situation? The term PHILE represents, phile represents loving. Hydrophilic means water loving. So, the metal oxide nanoparticles are in general hydrophilic. So, hydrophilic means these metal oxide nanoparticles have some strong connection, some strong attraction with the water molecule. You can make the metal oxide nanoparticle hydrophobic also by changing its surface, that is called surface modification. We can enter into more details in coming modules. So, in general, metal oxide nanoparticles exhibit the property of hydrophilicity. Metal oxide nanoparticles naturally have a hydrophilic surface due to surface hydroxyl group. See, for instance, if you are preparing iron oxide nanoparticles by a preparation method called co-precipitation method, there may be some free hydroxyl group on the surface of iron oxide nanoparticle. That hydroxyl group present in the surface of the iron oxide nanoparticle, this iron oxide nanoparticle surface having some OH group, this OH group can enter into hydrogen bond with the water molecule. So, if there is a water molecule, I can mark it as HOH. This hydrogen is partial positive, this oxygen is partial negative. So, there occurs some force of attraction between the hydroxyl group present in the surface of the metal oxide nanoparticle with water molecule. This increases their hydrophilicity. If I block the OH group present on the surface of this nanoparticle with some other capping agents, then this molecule can be converted to hydrophobic. So, in general, metal oxide nanoparticles are hydrophilic. You can convert it into hydrophobic also by suitable surface modification. Now, functionalization possibility. I just mentioned the fact that you can modify the surface of metal oxide nanoparticles by using some capping agents or some coating agents. Their surface, when modification with organic molecules or polymers or other biomolecules, enable different applications. If I coat a metal oxide nanoparticle with some organic ligands, and that organic ligands is connected to some drug molecules, then such a system is highly useful in drug delivery applications. So, you can use the metal oxide nanoparticle, the functionalized metal oxide nanoparticle in selective applications such as drug delivery, targeted therapy, etc. Another characteristic feature associated with metal oxide nanoparticle is the property of magnetism. You know what are magnetic materials? Magnetic materials may be paramagnetic, diamagnetic, ferromagnetic, and in the case of iron oxide nanoparticles, there is a special characteristic feature that is nothing but super paramagnetism. So, metal oxide nanoparticles exhibit different kind of magnetic behavior. Very few metal oxide nanoparticles are repelled by the magnetic field, and they are known as diamagnetic metal oxide nanoparticles. Most of the metal oxide nanoparticle exhibit strong magnetism, and we can now outlook on the magnetic feature or magnetism in metal oxide nanoparticles. Certain metal oxides like Fe3O4, CO3O4 exhibit super paramagnetic or ferromagnetic behavior, making them suitable for data storage and medical imaging, biomedical imaging. For instance, we have to consider the case of Fe3O4. Fe3O4 is a material whose magnetism is different from all other kind of magnetic materials. Popular magnetic materials include ferromagnetic, ferrimagnetic, paramagnetic, diamagnetic, etc. But far from that, this iron oxide nanoparticles exhibit a special kind of magnetic behavior. That magnetic behavior is called super paramagnetism. A material which exhibits super paramagnetism is said to be super paramagnetic. I am just mentioning about the super paramagnetism. You know the magnetic hysteresis phenomena in ferromagnetic materials. For a ferromagnetic material, there is two important characteristic quantities. They are coercivity and retentivity. A ferromagnetic material, if its coercivity and retentivity is 0, a new situation arises, and that situation is called super paramagnetism. So, what is a super paramagnetic material? A super paramagnetic material is a ferromagnetic material with 0 coercivity and 0 retentivity. Iron oxide nanoparticle like Fe3O4 exhibit super paramagnetism, or Fe3O4 is said to be superparamagnetic. I repeat the situation. A superparamagnetic material is a material with zero coercivity and zero retentivity. They are previously ferromagnetic, but in the case of the ferromagnetic material, there is non-zero value of coercivity and retentivity. If these quantities are zero, such ferromagnetic materials are said to be superparamagnetic. So, magnetism is a characteristic feature of metal oxide nanoparticles. Now, we are discussing some representative examples. We are taking zinc oxide nanoparticles, its preparation, its characteristic features to illustrate the general nature of metal oxide nanoparticles. So, we are taking zinc oxide nanoparticle as a representative example. In this module itself, we are take one more metal oxide nanoparticle for comparative study and reference. Now, we are taking zinc oxide nanoparticles for the discussion. Zinc oxide nanoparticles are widely studied metal oxide nanoparticles. Why this much study happens on zinc oxide nanoparticle? The answer is here itself. This is due to their versatile properties and broad range of applications. So, zinc oxide nanoparticles have so many characteristic features. Also, they have several applications. So, ZNO nanoparticle is one of the widely or thoroughly studied and highly useful metal oxide nanoparticle. Now, the exact physical and chemical properties of zinc oxide nanoparticle depend on different ways in which they were synthesized. This is a very crucial or most important point. Now, there are several ways to synthesize zinc oxide nanoparticles, and these are some important methods. The first most popular method for the synthesis of zinc oxide nanoparticle is the sol-gel synthesis. It is a widely used method to produce uniform sized and highly pure zinc oxide nanoparticles. And in this procedure, we are dissolving a zinc precursor, that is a zinc salt like zinc acetate, zinc nitrate, etc., in a suitable solvent like ethanol or water. And to this solution, to this salt solution in water or alcohol, we are adding a hydrolyzing agent. A reagent which is capable of donating OH minus ion, preferably NaOH, ammonia, NH4OH, etc. Addition of this hydrolyzing agent generates a gel. So, the solution is converted to gel now. And this gel on evaporation or removal of the solvent followed by calcination produces, calcination means strong heating, produces zinc oxide nanoparticles. So, in the sol-gel procedure, we have to take a zinc precursor like a zinc acetate or zinc nitrate to dissolve in alcohol or water to get a solution. Then we have to add a hydrolyzing agent like NaOH or ammonia. It is converted to a gel. That gel, on gradual evaporation of the solvent, produces dry gel, which on further heating or calcination produces the ultimate zinc oxide nanoparticles of high purity and controlled size. The next method we adopt for the synthesis of zinc oxide nanoparticle is hydrothermal synthesis. You are familiar with the hydrothermal synthesis for the preparation of the nanoparticle. It is, if you are using water as the solvent, then this technique is called hydrothermal synthesis. If some other solvent is used, then that procedure is called solvothermal synthesis. It is performed under high pressure and high temperature. So, this requires some specialized instrumentation. We learned about that instrument. That instrument is called autoclave, hydrothermal autoclave, or simply solvothermal autoclave. So, we can enter into detailed procedure for preparation of zinc oxide nanoparticle by hydrothermal synthesis. Use high pressure and temperature to control the growth of zinc oxide nanoparticle in aqueous solution. Mix zinc salt like zinc acetate with a hydrolyzing agent NaOH in water and heat the solution in a sealed device, special device, that is nothing but autoclave, and the temperature range is between 120 to 200 degrees Celsius. This heating continued for several hours, and as a result you will get zinc oxide nanoparticles as a result of final cooling. So, hydrothermal synthesis is a very popular method. Now we are discussing another method of synthesis of zinc oxide nanoparticle, that is nothing but microwave assisted synthesis. Usage of microwave radiation is highly efficient in accelerating the reaction, or microwave radiation enhance the rate of the chemical reaction. That means it is a highly time saving procedure. Mix a zinc salt and a reducing agent in a solvent. It is then exposed to microwave irradiation, or you have to place this solution, that is the salt solution along with the reducing agent, in a microwave oven. As a result of the microwave irradiation, these zinc nanoparticles are obtained and the nanoparticles can be separated after cooling. So, these are some important methods. Now, we are discussing the properties of zinc oxide nanoparticles. The size definitely ranges from 1 to 100 nanometer with a very high surface area. The shape of the zinc oxide nanoparticle may be in general sphere, but it depends on, the shape depends on the synthetic procedure we adopt. It may be sometimes rod-like, flower-like, sheet-like, etc. But the most popular geometry is nothing but the spherical shape. Crystal structure of zinc oxide nanoparticle. Zinc oxide nanoparticle has hexagonal woodsite structure which is thermodynamically more stable, and it contributes to physical as well as chemical properties. So, in general, zinc oxide may have more than one crystalline structure, but the most stable, especially thermodynamically most stable structure, is hexagonal woodsite structure. Optical properties of zinc oxide nanoparticles are here. It should be noted that zinc oxide nanoparticles, as in the case of many metal oxide nanoparticles, have band gap tunable by size, and in general it is having a band gap in the range of 3.37 electron volt. UV absorption capability is another feature of zinc oxide nanoparticle. They exhibit a strong absorption in UV region, making them highly effective as UV blockers and used in the preparation of sunscreens as well as coatings. Photoluminescence is another characteristic optical property of zinc oxide nanoparticles. They emit light in the UV as well as visible region, and this photoluminescence is attributed to the presence of defects, crystal defects like oxygen vacancies, zinc present in interstitial site, etc. These kind of defects, you are familiar with the crystal defects like Schottky defect, fungal defect, etc. that you have learned in your school classes. So, the photoluminescence in zinc oxide nanoparticle is due to the presence of intrinsic defects that may occur in its crystal structure. Thermal properties of zinc oxide nanoparticles are here. They exhibit high thermal conductivity, which beneficial for heat dissipation in electronic devices. They are highly thermally stable also. So, zinc oxide nanoparticles are nice thermal conductors and they have high thermal stability. Zinc oxide nanoparticles exhibit catalytic activity also. They are useful in photocatalysis, and in photocatalysis they are highly useful because they helps in the generation of ROS, that is nothing but reactive oxygen species when irradiated under UV light. This is highly useful in removing organic pollutants like organic dyes and is also useful in killing the microbes. Now we are taking Another representative example from metal oxide nanoparticle family, that is nothing but iron oxide nanoparticles. Iron oxide nanoparticles are tiny particles. They have a typical size ranging from 1 to 100 nanometers. They have great interest due to their unique properties, including magnetic behavior. I mentioned about the superparamagnetism. They are biocompatible and they are associated with the high surface to volume ratio. There are several types of iron oxide nanoparticles. The first most popular one is magnetite nanoparticle. It is Fe3O4. It is a ferrimagnetic at room temperature. It is known for superparamagnetic behavior when particle size is reduced to below a critical size. So, at ordinary conditions, magnetite exhibit ferrimagnetism. But whenever you reduce the size to certain nano regime, they will exhibit the phenomenon of superparamagnetism. You are familiar with the superparamagnetism, I have explained previously. Now, the second category is megamite nanoparticle. It is abbreviated as gamma Fe2O3. It is another ferrimagnetic iron oxide. It is highly chemically stable and often used in data storage, and magnetic nanoparticle can be used for biomedical applications. The last category is hematite nanoparticle, which is abbreviated as alpha Fe2O3. It is antiferromagnetic. It can be used in photocatalysis, for pigment preparation, and used for sensing gases. Now, the synthesis of iron oxide nanoparticles. There are several methods for the synthesis of iron oxide nanoparticles. First method is co-precipitation. This is the simplest and most widely used method for synthesizing iron oxide nanoparticles. Here we are mixing ferrous ion and ferric ion salt together and add a strong base like NaOH. They will provide hydroxide ions. As a result of the addition of NaOH, ferrous hydroxide and ferric hydroxide will precipitate together, and as a result, we will get iron oxide nanoparticles, which happens through this reaction. 2Fe3 plus Fe2 plus 8OH minus, it is obtained from NaOH. You will get Fe3O4 nanoparticle. It should be noted that all the reaction parameters should be kept under control, especially the pH. The pH of the medium must be between 9 to 11 for smooth generation of Fe3O4 nanoparticles. Thermal decomposition is another method for preparing iron oxide nanoparticles. This method is used to produce monodisperse as well as highly crystalline nanoparticles. Temperature improves crystallinity. So, thermal decomposition procedure yield iron oxide nanoparticles with excellent crystallinity. Use iron oxide precursors such as iron oxide coordination compounds such as iron 3 acetyl acetonate, abbreviated as FeACAC thrice, or another coordination complex of iron, that is iron pentacarbonyl. These two materials can be used as the starting material in thermal decomposition method. Take this material, subjected to high heating, they will decompose. As a result of that, iron oxide nanoparticles can be obtained. The decomposition of the precursors is generally carried out at a high temperature in the range of 200 to 300 degrees Celsius, and there must be a medium, and in many cases a organic solvent like octadecane is often used along with a surfactant such as oleic acid. The surfactants is used to stabilize the nanoparticle, which prevent the nanoparticle from agglomeration or precipitation. We are discussing the properties of iron oxide nanoparticles. Magnetic properties is highly dominating. Iron oxide nanoparticles exhibit unique magnetic features. This is due to their nanoscale dimension. Superparamagnetism shown by nanoparticles when the size is reduced in the range of 20 nanometer. So, magnetite nanoparticle exhibit the phenomenon of superparamagnetism when the size is reduced to the range of 20 nanometer. The iron oxide nanoparticle exhibit a characteristic feature, that is nothing but its biocompatibility. Magnetite and megamite are generally biocompatible. That means they will not create any toxic effect to living cells. So, these materials are highly useful for biomedical applications. Now, this is a consolidation of the properties of different iron oxide nanoparticles. Left hand side depicts the property like magnetism, stability, conductivity, biocompatibility, photocatalysis, etc. There are three types of iron oxide nanoparticles like magnetite, megamite and hematite. Magnetite is ferrimagnetic, it is moderately stable, high thermal conductivity, high biocompatibility and it is having low photocatalytic activity. However, for megamite, it is ferrimagnetic at ordinary condition, it is moderately stable, conductivity is also moderate, biocompatibility is high but minimum photocatalytic activity. And for the final category, that is hematite nanoparticle, which are antiferromagnetic at ordinary conditions. They are highly stable and conductivity is very low when compared with the other two, and they have low biocompatibility and at the same time they depict high photocatalytic activity. So, there are several types of iron oxide nanoparticle with the different characteristic features. Thus, by this discussion, we have studied general characteristic features of metal oxide nanoparticles along with the two characteristic representative examples. They are zinc oxide and iron oxide nanoparticles. Have a nice learning experience. Thank you.